This is an amplifier with a QBH1297, and it's a very simple thing. 2 connectors and the amplifier, and the amplifier is fed by 12 volts and decoupled here with a multi-layer 1 microfarad capacitor, so it should be well decoupled for RF. And then, since I'm testing sideband noise here, I have a very well filtered supply voltage. It's a 12 volt analog regulator, 7912 I think it's called, and it is followed by a 470 microfarad capacitor, then a 1 ohm resistor, and then a 4700 microfarad capacitor. So there shouldn't be any noise in the several hundred hertz frequency region. And furthermore, there is an inductor and a big capacitor on the input. And of course there are also high frequency capacitors on the regulator chip. And the amplifier looks like this. And if I open it, I have managed to destroy one, so I open it to have a look inside. There are 3 transformers, and then on the layer beneath it there are some capacitors, I think, and there must be some silicon also. I don't know. The data sheet for this amplifier looks interesting. It says 1 dB compression at plus 27 dBm and noise figure 6.5. And there is a noise figure versus frequency, so it should be more like 5 dB on 10 megahertz. To get balance in the interferometer, I have said to set an attenuation of 16 dB in front of this amplifier, which means that I'm sending 1 watt from the oscillator through this attenuator, which is set to attenuate by 0. So there is still 1 watt going to the hybrid here and splits, so there is half a watt, means 27 dBm entering the attenuator, which means that there is 27 minus 16, and that is 11 dBm entering the amplifier. And it should give 13 dB gain, means 11 plus 13 is 24 or 24 and a half maybe. I will look at the levels with the spectrum analyzer. The signal level is 11.8 dBm according to this spectrum analyzer. So it is close to 11 or maybe 12, and I don't worry about decibels on the decibels here. The output is 25.15 dBm. So the gain is something like 13.3 dB. And the data sheet says 13.5. And I can see, since I run in a interferometer, that there is some compression at this point. I haven't measured how much, but it's probably much less than 1 dB. Here is what I see on the interferometer. And I must mention that here I can see some noise close to the carrier, but before there was much more noise. Because first I had this schematic, just one big capacitor on top of the high frequency capacitor. And I didn't like that noise trumpet, which was about 10 dB above what I have now. So I added this 470 microfarad plus a 1 ohm resistor, and then this big capacitor. And that reduced the noise in the up to a couple of kilohertz range that was bothersome before. So remember, it is very important to have an extremely clean supply voltage to this amplifier, or to any other amplifier for that matters. I calibrate 300 kilohertz below the carrier, and look at the signal level I can observe on the carrier here, and I can read it out, and it shows 0. So this is the C level. Then I look at the injected signal here. I have to move it into the center of the passband, and it comes here at minus 80.0. So the injected signal is 80 decibels below the carrier. And then I look into the parsers. The 300 kilohertz lower signal is here, and I have set the calibration parameter here, so I can read minus 80 decibels, very close to that. And the details of this calibration you can see in previous videos. So I can switch off the injected signal, and here comes the noise floor. I have set the bandwidth to 1 kilohertz, and I can read here minus 149.5 means minus 179.5, 179.5 dBc per hertz at 300,000 hertz. And I go on and take other frequency separations and make this table complete. At 1 kilohertz separation, a 1 kilohertz wide filter from here to here is too wide because the noise floor is not flat enough. If I look at the level I see minus 142 means minus 172 dBc per hertz. But I will change the filter bandwidth. The narrower bandwidth does not change the calibration, so I switch off this calibration signal and wait for the noise floor. It runs much slower now because of the narrower bandwidth. Maybe I should speed it up a little, like this. And the noise level I see is minus 152.5. That means minus 172.5, not very different from what I saw with a 1 kilohertz bandwidth. The QBH1297 amplifier has been running for a long time now. Balancing is quite stable. It looks like this, and I haven't been here and touched the controls for 10 minutes. Now I will do an interesting thing. I change here by 1, 2, 3 decibels the power that goes into the interferometer. Balancing is completely destroyed, so I use this attenuator in front of the LNA at the output to come here. This is 40 decibels of attenuation. And then I look with the attenuator on the other path of the interferometer and step by 2 decibels. So 2 decibels one way makes that, and 0.2 decibels 0.2 decibels. The other way goes here. So the change is less than 0.2 decibels, maybe 0.1 or so. I will do the balancing and then look at the noise. I have restored zero attenuation and turned the balance so I have proper suppression of the carrier in the interferometer. And then I look at the Linrod screen. Of course the noise has gone down, but it has gone down by far more than 3 decibels. It seems. I will wait to get the statistics. With 3 decibels less input signal, the noise is down by 8 decibels. So obviously performance has improved, and I will repeat the measurements. I have done at plus 12 dBm approximately, and I will do it now at approximately plus 9 dBm to see how much is the difference. This is a separation of 2 Hz at a bandwidth of 1 Hz. And I have calibrated properly, and the noise I read is minus 141.7, and that is directly dBc per Hertz because it's 1 Hertz bandwidth. I have improved supply voltage filtering by adding one more 1 ohm resistor and one more 4700 microfarad capacitor. And now I will look if there is any difference due to this. This is at a frequency separation of 1 Hertz. And you can see the noise floor is fairly flat, close to the carrier, while it's sloping fairly fast, some 10 Hertz away. And at wider range, 10 kilohertz, 20 kilohertz, it has a fairly linear slope, and then it flattens off at larger separations. So I don't understand any of the theory behind this, but I will make an experiment with better filtering of the supply voltage. Here are the results of my first measurements. The lower trace is at full power and the red is at 3 decibels less. Plus 12 dBm input and plus 9 dBm input. And of course, at wide range the noise figure dominates, and therefore lower power is less good. At close range, lower power is much better. And there are some little problems with how I made the measurements, so some points are missing. It is the circles with the extra filtering and the crosses without, and there was an error in some points. But anyway, this seems to indicate that lower power is better. And I stopped the measurements at full power at a bandwidth of 20 Hertz, and now I have done much better, and I will show that with the improved filtering. Here is what I have found now in the QBH 1297. The noise is fairly constant from 1 Hertz up to about 10 Hertz. Then it drops rapidly, and at 100 kilohertz we start to see the influence of the noise figure at the level of about minus 180 dBc per Hertz. And at 10 Hertz separation the level is minus 142 dBc per Hertz, and then it drops rapidly. So I will try to make a better filter for the power supply to see whether something changes. I have filled the box with 4700 microfarad capacitors, and maybe this will change things. I will look at that. The bigger capacitors clearly makes the noise a little bit lower, in the range, let's say 3 Hz to 200 or 300 Hz or so. Here, the difference is not big, it's only 1 or maybe 1.5 or 2 decibels. And the capacitors are significantly bigger, but a factor of 2 should mean 3 decibels, and that's not what I see here. So I don't wish to proceed further with this. Probably the capacitors have some noise voltage across them because there is some leakage currents. And studying this in detail goes in a direction that I don't want to spend my time on. But the supply voltage is a very important factor with this kind of amplifiers. So what I see is here, that's the noise floor, minus 180 or a little bit more dBc per hertz. That's given by the noise figure of the amplifier. And at close range, say 1 hertz, the noise is minus 135 dBc per hertz. And at this close range, the noise is not depending on the size of the capacitors. It's probably defined by the voltage regulator. Well, at 3 decibels less power, plus 9 dBm input, performance at a very wide separation is of course 3 decibels worse. But at close range, the green curve, performance is much better, or significantly better. Means something like 5 decibels at 5 hertz separation. Now, what I see here for the QBH 1297 is not very impressive. If you look at this curve, where you can see where 140 is, and then compare with this diagram, where you can see that the amplifier with BUK 75150 that I've shown in a previous video is much better, and it also goes much lower here. It's because it's an amplifier with a similar noise figure but much less gain and much less sideband noise. Now, an attenuator might easily be much worse. The AMC 147, a commercial amplifier, is not so good. And then you can find an MMIC from, I don't remember the manufacturer, but it's really bad. So selecting the proper amplifier, if you're interested in low sideband noise, is a delicate matter. And I actually don't know enough to say more about this, but I'm sure there is much more to say about it.